Alrighty, thank you ladies and gentlemen for joining us this afternoon. We'd like to welcome you to Yokogawa's Analytical Web Seminar on the pH and ORP basics and understanding pH and ORP theory, maintenance, troubleshooting, and kind of a little bit into the product selection, in essence, of measuring electrodes and reference electrodes, the different types of forms there are. So we'd like to thank you for taking the time for attending today, and we hope you find this seminar helpful and informative. My name is Sherilyn Marlowe. I work here at Yokogawa in the Analytical Product Division. Before we begin, we would like to go over some housekeeping issues. The audio part of the seminar can be accessed through the teleconference or the info tab on your WebEx Manager window or through your PC speakers. The seminar will last about an hour. We're thinking about 45 minutes and then a 15-minute Q&A. Don't worry if the question and answers are going pretty fast and flowing. We're going to stay and answer as much as we can. If we don't, we will contact you directly, either via email or phone call from either myself or today, our presenter, Nick Nichols. So during the seminar, if you want to ask your questions, go ahead and fill them out into the chat or the Q&A. And then, as you know, at the end, I'll go through them and I'll ask them and we'll answer them. So today, let's go ahead and get this started. Our featured speaker today is Nick Nichols. He has worked here with Yokogawa for 29 years. Prior to working for Yokogawa, he's worked about 18 years at Rosemont. All of this time, he's worked with liquid analytical products for both Rosemont and Analytical. So before we go ahead and get this started, let's hand it over to Nick Nichols.
All right. I'd like to extend my welcome to everybody that's listening, and looking at the numbers, there seems to be a fair amount of interest in this topic. So what do you say we just get started? Our goal today is, as you can read, we want to provide some information to help you get a reliable measurement for pH and ORP. There's a wide variety of industrial applications which rely on pH and ORP, and our intent is to review some key issues to help you achieve that successful measurement. We'll discuss some solutions and procedures, ways to handle those issues that we have seen and you have run into, I'm sure. Then we're going to share some tips and techniques that we picked up over the years for troubleshooting and maintenance. The result, again, is that we hope to help you get the best measurement accuracy and reliability for your particular process, whatever that may be. So we're going to start out with pH. And pH is a key measurement in any number of areas, and you can see why. I mean, it's used from everything from controlling bacterial growth, involved in inorganic reactions, product quality, and basically anywhere where water is used either directly or indirectly, you can pretty well figure there's going to be a pH application or two. This is just kind of a short list of a number of common applications for pH, so you can see it's spread all over the map. Again, wherever water is used, you can bet your boots that there'll be some pH measurements and pH problems as well. So what is pH? Basically, what are we measuring when we measure pH? What makes a liquid acidic or basic? Well, another name for a pH electrode is a specific ion electrode for hydrogen. When we measure pH, we're actually measuring the hydrogen concentration of the solution. You know that little P in pH? Well, that stands for power. It's a Latin word, pondus, but it means power. And the H is obviously for hydrogen. Therefore, pH is the power of the hydrogen component in the process. And as you can see from the chart, a pH value of 8 is about 10 times, not about, but exactly 10 times more basic or caustic than a 7, and it's 100 times more caustic or basic than a pH of 6. So we need to be mindful that even small changes in pH can be a significant change in the chemical strength of the process. We're talking about the pH scale and the relationship between the level of hydrogen, the H+, and the hydroxyl ions. If they're perfectly balanced, there's an equal number of them. We have what is called neutral pH or 7 pH. And there is diffusion that goes on in water when chemicals are added, and sometimes only when temperature changes. And when that happens, the relative acidity or alkalinity will change. So if there's more H plus or hydrogen ions, and there are OH negative or hydroxyl ions, and it's said to be acidic. And this is an example of, let's say, carbon dioxide gas being dissolved in water. You can see that it's got a pH of about 3. In the other direction, if there's more hydroxyl ions than there are hydrogen ions, then it's considered to be a basic or caustic application. pH scale is one that we'll talk about how it's developed, but you can see here that we kind of need to take what we're looking at here and get a simple definition of what we're trying to measure, so we can hold on to that as we go through. And so really pH is just the acidity or alkalinity of an aqueous solution. Now the key point here is that in order to measure pH, you have to have at least 5% water, 5% H2O. Here we get requests once or twice a year. Somebody calls in, they want to measure the pH of something like jet fuel. What they really want to measure is the water content, and they think by somehow measuring pH that's going to equate to it. The reality is that unless you've got 5% water, you're not measuring pH. You may be measuring something, but it's not pH. And you can see on the scale here, there's several different liquids and their relative acidity or alkalinity. And I was wondering if you mixed one beer with one gin, would that neutralize? I'm not sure. And on the right, we've listed some common chemicals that are used in industry to control or neutralize pH. You have hydrochloric acid and sulfuric acid that will dissociate and add hydrogen ions, making the solution more acidic. You've got sodium hydroxide, which dissociates and gives you more hydroxyl ions to make it more caustic. And these are used very frequently in a number of places, in different strengths to control and neutralize the pH that's in the process. You can't have a pH training without visiting our buddy Nernst, and he has done a lot of work. He needs a new hairdo, but he's a pretty smart guy. And what he did was he developed the theory and then followed through to give us what we call our slope. It's a relationship between the step change in pH, and for every step change there's a 59.16 millivolt change when it's measured at 25 degrees C. Now, I mentioned slope, and I want you to keep that in mind because we're going to talk about that later, because this scale is important not only for the measurement scale we use, but also we use it when we do calibrations of pH electrodes. If you notice on the graph on the right, it's looking at pH at different temperatures, and it shows that the relationship is different as the temperature changes. And that's something we also need to take into account, because pH is affected by temperature increases or decreases. Mainly, we see the effect on increases. What happens is that as the temperature increases, that hydrogen bond tends to break and cause the process to change in pH value. Now, there's two important effects that related to temperature that we're going to discuss, and the first one is the effects of the temperature on the glass electrode itself. This graph shows the importance of temperature compensation for its effects on the measuring electrode. That's the little bulb on the end of the glass body. That pH glass is sensitive to temperature change, and if it's uncompensated, you can see it's a change in the pH as much as, well, they got 0.2, 0.6 pH, when there is actually no change in pH, just a change in temperature. So pH measuring electrodes are compensated back to 25 degrees C usually, using electrodes such as a PT100 or PT1000, which measure the temperature, and then through the processor does its math and corrects for the effects on the glass electrode. Now, you notice at 7 pH, the electrode has 0 millivolt output, and really there, temperature compensation is not required. But as you get further away from 7, in either direction, the effect becomes more prevalent and more intense. The second effect has to do with the temperature characteristics of the process itself. This is referred to as the solution coefficient. Process solutions, especially caustic solutions, tend to have a temperature coefficient, which means as the temperature changes, the pH reading will change by some amount. Now, you notice this most often, or I've noticed it most often, when there's an argument between the lab and the process gentlemen, that their two readings don't match. And this occurs because the sample measured in the lab is often measured at a lower temperature than the process. For example, let's say we have a measurement online at 60 degrees C and it reads 8 pH, while the lab is reading 25 degrees C at 9 pH. Well, what's in play here is that this particular process has a coefficient. It changes as the temperature changes. And it's a relatively simple procedure to determine, one, whether there's a coefficient, and two, to calculate that coefficient, because what we're looking for is the pH shift per degree C. And most analyzers, or many analyzers, allow you to be able to enter this value into the unit so that the pH reading will automatically be compensated for. And the result is that the online reading and the lab reading will match. While we're talking about analyzers, let's take a minute to look at what is actually required to measure pH, to make a pH loop. Obviously, you need an analyzer that converts that raw input signal from the sensors and calculates the things that need to be calculated and displays and transmits the pH and associated values like temperature. Then you need the pH sensors, which are 4 in number. You've got the pH measuring electrode, the reference electrode, the temperature electrode we referred to a minute ago, and also something called solution ground. Now, these can be either separate electrodes or they can be all contained together in one, all in one body. The cables themselves, obviously, they can be separate, and you can disconnect them at the sensor, or they might be integral as the all-in-one style has. But if you have separate electrodes, you do need some sort of holder in order to get these online. Now, most of the all-in-one sensors, they usually have threads on them that you can use to mount the sensor, or they come with some sort of an adapter that they're mounted into, which will allow them to be taken offline more easily to make routine maintenance and calibration easier. So now we're going to dig a little deeper into the basic pH measurement circuit of the reference and the measuring electrode. We've omitted the temperature and solution ground for the moment, just to keep things simpler. You can see there are voltage potentials depicted, and several of these can cause adverse effects on the accuracy of the measurement, so we need to pay attention and to do what's necessary to protect and correct against those. The total voltage of the circuit is the algebraic sum of these, and since we use identical silver-silver chloride elements within both the glass electrode and the reference electrode, the E3 and the E4 values, voltage values, are equal, but they're opposite in polarity, so basically they cancel out. The little E5 that you see here near the junction of the reference electrode is a diffusion potential, which occurs, because of the mobility of the KCl solution moving through that junction. And it's usually, if everything's working right and there's no issues, it's a very small voltage and really can be ignored. The remaining two, E1 and E2, are the inner and outer, either side actually of the glass electrode, and The inner is basically a constant. That's the buffer solution that's in the glass electrode that is about 7 pH, exactly 7 pH. That's a constant. So now we're down to the only potential that we really are concerned with, the only one that's affected by changes in pH or should be affected by changes in pH is E1. And that's what we want to do. We want to eliminate all the other ones from affecting that measurement so that we can get an accurate, reliable measurement. But the process doesn't usually help out. I mean, there can be coating of that glass electrode. There can be plugging of the reference junction. There can also be that the process we're in is pure water, which means that there are basically no ions in it, and so there's no real electrochemical connection between the reference and the glass. So that's a problem to deal with, and we'll talk a little bit about flowing junctions and how that helps overcome that. There can be pressure spikes on the process that will cause a pumping effect and pump out that KCl solution in the reference, changing its effectiveness and accuracy. And then there's the ides of March. Well, that's not true. There's a bunch of ides, sulfides, cyanides, bromides, all of which will connect and coat with the reference electrode because it reacts with the silver to form a silver sulfide, which again is going to cause errors in the measurement and give us an inaccurate reading. We'll drill down a little deeper on the measuring electrode. The glass itself is a special formulation, so it's sensitive to pH. Typical electrode bodies are mostly glass, but I've seen some that are plastic. Inside the electrode, we have that silver chloride wire, and it's immersed in an electrolyte. That's a KCl solution buffered to 7 pH. Now, both wetted surfaces, inside and out of the glass electrode, they create a little gel layer or a thin layer of a solution, and that means that we need to keep this electrode wetted, and that's why you see when you get your pH electrodes, they all come with a little boot on it. That's to keep the outer side of the glass electrode wet, because if it dries out, you're not going to make a measurement because it's basically an open circuit. Now the fill solution inside, again, it's 7 pH. The process solution is what we want to see change. And if we stick it in a 7 buffer, there's no difference of potential between the inner solution and the outer solution, so we get a 0 millivolt output. Remember, we talked a little bit earlier about how temperature affects it, so as the temperature increases, the voltage change, which is shown on the right, 59.16 per pH step, could be as high as 60, 61 millivolts. So that's why we compensate the electrode, the pH measuring electrode, with a temperature electrode back to 25 degrees C. We can't measure this voltage directly. We need to introduce a reference voltage and a way to complete that electrochemical circuit. So we'll touch on that in just a minute. But here's some typical problems that you're going to see with the measuring electrode side. If you get an electrode and the tip has a hairline crack in it, you're going to get a nice stable reading somewhere near 7 pH. If you don't have an appropriate diagnostic system, it may not look like there's an error. It just may look like a very stable reading. However, it's a very false reading. Coating, aging, all affect the electrode and cause it to be sluggish and inaccurate, and higher temperatures tend to shorten the sensor life. Okay, now let's look at the other half of the measuring loop, the reference electrode. In order to measure the changing pH, we need, again, a stable reference value to compare against. And Mr. Nernst, he was having fun in his garage, I guess, but he took a metal, which is the silver wire shown here. He combined it with its insoluble metal salt, that's the silver chloride pin, and immersed it in a salt solution, that's the KCl electrolyte, and that can be either a liquid or it can be a gel. But as long as the chloride concentration remained constant, he found out that this combination of elements would produce a constant millivolt potential. Now, that constant potential is not affected by changes in the process. However, it is affected by the constituents in the process that can cause things like the poisoning of the silver element, the KCl being depleted, in other words, pumped out through the junction, or the junction itself being coated or plugged. So all of those things that can happen to the electrode will cause it to have errors when, in its pristine state, it does supply a perfect reference electrode voltage. However, when we talked earlier, there's a second function, which is the reference electrode has to provide an electrochemical continuity between itself and the pH measuring electrode. And it's through that liquid junction, since it's porous, the KCl internally can pass through and then in turn come in contact with the measuring electrode. But this also means that that internal element is open and can be affected by the process, as we just described, from poisoning and depletion of the KCl. The liquid junction, it does offer some protection to the electrode. It slows down the ingress of the process and the poisoning. But if the junction does become plugged, as we mentioned earlier, or coated, by the process, there will be an increase in voltage potential, which is in turn going to give you an inaccurate measurement. As we said, again, we'll restate it so we all keep it in our minds that this reference has to provide a constant voltage and complete the circuit. The electrodes typically are either gel-filled, as I mentioned before, or liquid-filled. The gel-filled is an electrode that can't be refilled. Typically, it's just diffuses through the junction at a slow rate until it depletes and is no longer useful. The liquid electrolyte or flowing reference does solve some problems. The liquid KCl is usually under pressure so that it diffuses out through the junction and not allowing the process to get back in. So there's several types of junction depending on the application that we're addressing. There's ceramic, there's a porous Teflon, glass sleeve. The diffusion type, which is the gel-filled, which is used in about 80% of the applications. They come in various single and double and triple junctions, all of which are designed simply to slow down the poison effects of the process on that silver element inside. Positive pressure or flowing junction electrodes are a great approach. The design forces a steady flow of the internal KCl in that reference electrode out through the junction at a higher pressure than the process. So consequently, the process can't enter through the junction as long as that pressure is maintained. And by keeping the process out, the silver element's protected. Now, this design also helps to keep the junction itself clean because it's flowing. And obviously, the KCl has to be replenished, so there is some maintenance required. But also for the positive pressure, they're very useful for pure water applications. Again, there's no conductive material in pure water, and in order to make an electrochemical continuity between the reference and the glass, we need something that's conductive, and the KCl is, so if it's steadily coming out, then we do have our electrochemical circuit. There are also some accessories or alternate methods that can be used to reduce some maintenance time and also maintain the benefits of a flowing reference. One example is called a salt bridge. This is a variation on the positive pressure approach where a standard reference electrode is placed in this chamber. You know, see that inside the chamber here where that's filled with KCl, and then what we call a dummy electrode is actually the electrode that's put online. Now that dummy or empty electrodes connected back to the chamber via tubing and some sort of polyflow or type of tubing, and the chamber itself is pressurized to a level that exceeds the process. So KCl is forced out of the chamber, through the tubing, through the empty tube, and into the process. Now, this keeps KCl flowing out, doesn't allow the process to enter the actual reference electrode, and the dummy electrode has a junction, as shown here, to reduce the flow rate so that it doesn't deplete too rapidly. So something to consider here is that we're using a standard reference electrode back in the chamber. It sits there safe and sound, and it's protected by that path that the process has to come through the dummy electrode, through the tubing, through the KCl, and actually through the junction of the electrode itself before it ever gets to poisoning that internal element. So some of the typical problems we've looked at and we're talking about here for reference electrodes are plugging and poisoning, and pure water, there's something called stray currents that because the electrode is a lower resistance electrode, that if there's stray currents on the process, it's the path of least resistance, and so those stray currents go to the reference electrode, causing noise and shortening its life. But even looking at all of these options of things to correct some of these difficulties that we've discussed, they may not be sufficient. And in that case, we do have another option, which we call the differential pH sensor. To review a little bit, again, the conventional reference, it's independent of the process effects. That means it'll give you a nice steady voltage as long as there's no poisoning, plugging, electrolyte depletion. But a cation or electrode is dependent on the process because it's dependent on the salt level of the process. We'll talk about that a little more in a minute. But it does also suffer a little bit that it has a reduced measuring range. It may be 2 to 14 or 3 to 11 depending on which process we're in. But there's no junction, there's no conventional problems, there is reduced maintenance, and it can be, there are a couple of different versions, but it may only be a single point calibration where conventional electrodes should always be a dual point calibration. So there are some advantages there. Now, what we were referring to about the salt concentration is that this being a cation reference side, it moves with the concentration of the salt in the process. It's not independent of it. However, it's going to take a 25% increase in whatever that salt concentration is to get about a 0.1 pH change in the measurement. Should the salt content change like 40%, then you'd have, as you can see here, a 0.15. Processes above about 5 grams per liter are very good and very stable, and to have a 25% increase is huge. So above that level, they're relatively stable, and there's very small change in pH reading. If you're below that value, you have to make sure that the salt concentration remains stable. If it remains stable, then there's no pH change. So if these things are taken into account and can be accomplished, then the differential sensor is something that's a good option. Again, there's no silver element on the reference side, so there's no poisoning. There's no junction. There's no chance for depletion. But as we said, the trade-offs are, it's not a true pH measurement because the reference does move with the process and affected by the cation changes, and it does have a reduced measurement range. But it is a possibility. It is something that is a tool in your bag if you have an application that it's suited for. Works very well. I want to put this up. This is to show that there's an effect, obviously, on life due to increases in temperature. There's a wide range of sensors out there, and they all have varying temperature specifications, some rated to 80 degrees C, some to 130 degrees C. But this doesn't mean that that sensor can be, let's say it's designed for 130 degrees, that it will get the same lifetime at 130 that it would get at 25. Higher rated electrodes will last longer than electrodes that their upper end is not that high, but even those higher electrodes, 130-degree electrodes, will last a lot longer if you can find a place to mount them in a lower temperature. And this graph is just a reflection of our experience. It's not a nerd-like scientific study. It is simply a typical life expectancy that you should keep in mind, so that if you have an option to install a sensor in an area with a lower temperature, you're going to get a longer life. When you're looking to put in a loop, the sensor is obviously the most important, and the best way to get the best sensor for it to fit your application is to know what the process conditions are, the temperatures, what the chemistry is there particulate involved? Because each one of these has an associated problem, shortened life, abrasion, you name it. So by knowing your process and knowing the things that are going on in there that can cause problems, you're able to pick the right electrodes or the best electrodes for that particular application, so you can get the most accuracy and obviously the longest life. All right, now we're going to move into talking a little bit about maintenance and calibration of pH. We'll start with cleaning. I believe I've seen in most cases a lot of folks go out and no matter what, they clean and then calibrate. Well, that's not necessarily a need. You do need to calibrate a pH loop at least every 3 to 4 weeks for the aging of the electrodes. Nothing else. That's just basic. No matter what, you have to calibrate for the aging and deterioration of the electrodes. But cleaning may be the only thing that's required in between, and the way to do that is we've found that, the rule of thumb is whatever your application is, in order to clean, you use whatever works. But we found that a 5 to 10% solution of hydrochloric acid works best in a wide variety of applications. Obviously, you rinse the electrodes, you clean them, then you rinse them again to get that cleaning solution off, and then you put them in a pH buffer and you make a measurement. Now, if the measurement's within plus or minus 0.03 pH, which is a basic range for efficiency of the electrode, then it's clean, it's functional, and you can put it back online, which saves you some time. If you make that measurement and it's beyond that 0.03 pH, then yeah, 2-point calibration is in order. Now, one thing I'd like to point out here, a lot of folks I've talked to do this. When you're rinsing the electrodes, use plain water, not deionized water, because this can, especially if you leave the electrode in there to soak, the reason is that deionized water tends to pull the salts out of the reference junction, depleting it and creating an increased junction potential, and it's going to take a while for that effect to go away when you get it online, because those salts need to be replenished. If you're rinsing it in DI, that's fine. If you're soaking in it, I would consider just soaking it in tap water. In calibration, like I said earlier, every pH sensor requires calibration for aging of the electrodes or deterioration, and that's done about once a month. More aggressive processes are going to require that there's more frequent maintenance and calibration. And by aggressive, we're talking about those applications where the chemicals are strong or aggressive, or there's coating, or there's elevated temperatures. You should always use fresh buffers, and because they are the baseline. If the buffer's wrong, you're calibrating to an error. And buffers come supplied as liquids, those and powders, but the liquids, they all have a limited life, especially the alkaline or the higher pH buffers. So they need to be used when they're open, to be used quickly, because CO2 can affect those buffers and cause their value to change. And after you complete your 2-point calibration, and we recommend using a 7 and a 4 buffer, A final check for the calibration can be done by putting the sensor back in the first buffer solution and seeing if it's still accurate, and if it is, fine, and if it's not, it may be that you need to repeat the calibration again. Buffers are, like I said, the baseline for assuring your measurement loop is accurate. If the buffers are bad, the calibration will be inaccurate, and the subsequent online measurements are going to be inaccurate as well. Now, there are two types of buffers available in the marketplace. They're called NIST, National Institute of Standards, and NIST Traceable. The NIST buffers are the most pure and have the longest life before becoming inaccurate, but either type of buffer can be used. The NIST Traceable 10 pH buffer is the least stable NIST buffer, or the least stable buffer of all the common ones that we use today. So you need to make sure if it's one you're using that you use it while it's new, fresh, and use it immediately. And here's why there's a difference. Remember back when we didn't have digital? Probably some of you don't, but some of us do. We had analog meters. And so to calibrate a pH loop to a 6.86 or a 9.18 would be nearly impossible. So what the manufacturers did was they took material, basically for the 6.86, and added to it some material to cause it to read 7, which is a contaminant of some sort. And the 9.18, they did the same and raised it up to a 10. Well, a buffer is only a buffer and remains accurate as long as it's not contaminated. So if you already add a contamination to it, you're going to decrease the amount of effectiveness and the amount of time it's useful. And you can see that for a 10, that's almost a full pH away from the 9.18 where it started. So that's why it's the least accurate, the least reliable buffer that's out there. Calibration. A grab sample calibration, and I'm sure most of you that work with the pH loops have probably done one. All you're really doing there is calibrating for the reference side of the electrode or the zero side. And what happens is the perfect red line there is that slope of 59.16 millivolts that Mr. Nernst put together for us. And when I go out and took the grab sample and it said 4.5 and I adjusted my pH loop to 4.5, that's the blue line, I'm accurate right there. But if the pH changes up or down, I'm not accurate anymore. I'll have to go out and do another 1-point calibration, and then I'll be accurate at that point. So we recommend 2-point calibration because really, if you want to think of it this way, you're doing 2 calibrations. The first part of it is calibrating for the reference electrode, the second part for the glass electrode, and they are in combination, but it's just an easy way to think of it. Because when you do a 2-point, you still do the first part. You still put it in the 7 buffer and zero it out. But then you put it in a 4 buffer, and you calibrate it so that that combination of electrodes through the analyzer now looks like a perfect Nernstian slope. It matches that slope, and that's the idea, is that we want those electrodes to look like they're perfect so that we will get an accurate measurement, so we compensate for any error that they might have. Now, we haven't talked about the solution ground electrode, but it's an important one. In years gone by, I think most people have gone to high impedance dual amplifiers, but it used to be that there were single-ended amplifiers where one side had the measuring electrode, which is a high resistance, and the other side had the reference electrode, which is a low resistance. And being a lower resistance, that reference electrode was the shortest path to ground, so straight currents and voltages and would go through that electrode, causing it to be unstable and shortening its life. Well, when they finally got around to using 2 differential high impedance, meaning it measures high resistances and high impedances on both sides, and putting a solution ground as a common point in between, it eliminated the effects of the process on the reference electrode, and they instead would go through the solution ground. So that was a big plus. But it also offered us some significant advantages because we are now able to measure each electrode, the glass electrode, independent of the reference electrode, and gain some information that we can use to make sure we feel confident that our process is working well and is accurate. What we're able to do by making that measurement is determine the amount of offset from zero that the reference electrode is, and usually there's a range of something like it shows here, either minus 120 to plus 120 millivolts. You want your reference to be as close to zero as possible, but it can be affected by the process to where it is perhaps 30 millivolts or 60 millivolts away, and then compensated electronically to make it look like zero. Your glass electrode, they're come in at usually in the high 90s as far as efficiency or accuracy according to the Nernstian slope. And as they get away from that, they become less accurate and sluggish, but they can be adjusted as well. And after a 2-point calibration, you're able to read the asymmetry value and the slope value, which tells me the health and wealth of my measuring and reference electrode. So it tells me whether I need to change it. It tells me how fast it's deteriorating. So it's good information because now I can validate that it's a good or a bad electrode, so I get this confidence that I'm verifying my measurement by being able to say that all the components in there are working well. In addition, we get some great diagnostics. We can tell if there's that cracked or broken electrode that reads 7 pH. Well, now that if it cracks, you get a signal that that's happened. You can see the buildup on the reference junction, so that you know, well, ooh, I need to come out and clean it because it's changed in the last 2 or 3 hours. The process has begun to code on it. So there's some excellent information that help us with maintenance, with tracking the life of our probes. And so when you're considering your equipment, make sure that there's some form of effective diagnostics included so that you can take advantage of these things. There's a little chart of troubleshooting tips that actually the diagnostics would lead you to, but if you don't have those, they're kind of a rule of thumbs to help you find where the problem is, whether it's a noisy response or drifting measurements. Usually it's going to be some sort of coating or plugging or poisoning, which means it's going to require some cleaning and or calibration on some sort of regular frequency. And just as a rule of thumb, if you were blindfolded and handcuffed and you had to make one choice to correct the measurements and get it back online, 80% of all problems with pH are the reference electrode. And you can see why. It's the one open to the process. It's the one that can be poisoned or plugged. So, but most of the time, that's where you're going to be looking and finding the problem. I want to talk a little bit about storage. I'm sure you all store your electrodes correctly, but we talked earlier about the boot that the probes come in to keep the outer side of the pH measuring bulb wet. Well, there's a little air pocket in the pH electrode. It's an expansion bubble that if you store this lying flat, it can migrate to the tip. And we talked about both the inside and the outside of that bulb needs to be wet. And if that air bubble's there, then obviously that's not happening. It's not a big problem. You can either store the electrodes tip down, or you can treat it like a thermometer and shake it down a couple of times so the bubble moves back, and then you're good to go. We get a lot of questions where someone says, I just took my probe off the shelf and it's slow and it's not responding, and I think I need a new one because this one's not working. Well, again, these are sent out in booths with a KCl and sometimes a KCl mix of a buffer solution. And if they're sitting in the stores, that can put a coating on it. Doesn't affect the electrode life, it just puts a coat on it. So what we need to do is clean the electrode. So even if you're taking it new out of the box, a rule of thumb is to always clean the electrode first before you put it online or attempt to use it. So we've gone over a number of areas. We've talked about some basics and that this the pH electrode is really a specific ion electrode. Talked about temperature effects and how it affects the electrode itself and how the process also can have a temperature coefficient. We looked at the solution ground and the value that that gives us when reducing noise and giving us the ability to do online diagnostics. Talked a little bit about maintenance and some recommended procedures, but we also talked about some different electrodes and accessories that can be used for when we've troubleshot an area and found out that what the problems are. There are alternatives that we can turn to put the right sensor online to get the best measurement with the least, hopefully, the least amount of maintenance and the greatest accuracy. All right, now for the fun. Now we're going to talk about ORP, or oxidation reduction potential. ORP, or oxidation reduction potential, has fewer applications where it's used, but those applications are very valuable measurements, and this ORP is a valuable control parameter that is used. And you can see here some of the typical applications, and they're not necessarily fun places with cyanide and chromium and all that going on. This is definitely a measurement where we need it, it's effective, but we also need to pay attention. You will find out as we go through here that ORP and pH have a number of applications where they're teamed up, so we'll talk about that too. There's a lot of similarities between pH and ORP. They're both electrochemical. They require high impedance circuits usually. They both have silver, the common configurations. Both use the same silver-silver chloride reference electrode design. The ORP is different on the measuring side, obviously. It is a noble metal, either a gold or a platinum usually, and it does have an advantage in that it's not affected by temperature, so there isn't a temperature electrode necessarily required when you're measuring ORP, although some folks, you put them in anyway so that they can see the temperature on their analyzer. What is ORP? Well, it goes by another name, redox, which refers to the fact that within the process being measured, both reduction and oxidation are occurring simultaneously. So you can't have one without the other. If one species undergoes oxidation or loses electrons, then the other species must accept them, and is considered reduced as it gains electrons. And there's a little simple way to remember that, and this is oil rig, where oxidation is lost and reduction is gained. That ought to help in a trivia contest somewhere. Okay, what is ORP? Well, we need a simple working definition. So it's the measurement of a solution's capacity for electron transfer known as oxidation or reduction displayed in millivolts. Okay, it's not that simple, but it's very descriptive. While pH indicates how acidic or basic a solution is, based on the hydrogen ion, ORP indicates that the reduction-oxidation status of a solution based on the total collective electron activity within the solution. This is a part of the ORP scale. Usually it's the full range is 1500 plus or minus. The pH scale, an acid is defined as a substance capable of liberating hydrogen ions, and a base is a substance capable of absorbing hydrogen ions. So every acid has a complementary base, and when you look at the pH scale at 0 millivolts, it's neither acidic or alkaline, but as you move above, the solution is considered to be acidic, and when you move below, it's considered to be alkaline. Okay, ORP can be defined in the same manner. A reducing agent is capable of accepting an electron, and an oxidizing agent is capable of losing an electron. Therefore, the stronger the reducing agent, the more negative the ORP, and the stronger the oxidizing agent, the more positive the ORP. For example, acid permanganate is strongly oxidizing and tracks electrons, and so it's highly positive, and sulfite solutions, which are strongly reducing and pushing electrons into the electrode, are strongly negative. Conventional ORP, as I said earlier, uses the same reference electrode as a pH system does. However, since that measuring electrode, unlike pH, isn't affected by temperature, then we don't need a temperature electrode. And as you can see from the slide, our buddy Nernst defined the electrochemical properties of the loop. And again, we're only interested in that E1, or the voltage present at the measuring electrode. All the same problems we discussed with the pH reference apply here, because we're using the same pH reference, apply here when we're measuring ORP. The measuring side, typically it's either a coating issue or a corrosion issue, because it's a metal, it's a gold or a platinum. Now, all the same solutions we discussed for the reference side, flowing junctions, salt bridges, and all of that still apply. However, there's one unique configuration that is used primarily for those applications where we need to eliminate the effect of pH changes on ORP. And you can see here in the chart there's the same ORP solution, but at different pH values, and they're obviously not the same. And that's using a traditional reference. So somehow we would have to compensate for those differences with a pad and pencil, do the calculations and figure out what the actual ORP we're getting is. But if we were to put a pH measuring electrode as the reference electrode, it will basically eliminate those H plus ions, the pH changes, and ride on those, if you will, leaving only the ORP values. And this is common in cooling tower applications where pH, we add acids to control corrosion, and we're also using ORP to indicate the power or the effectiveness of chlorine that's used as a biocide. So we don't want to add the changes in pH to that. We want to just see how effective the chlorine is. So we need to eliminate those pH changes. So we put a pH electrode on the reference side, and it works really very well. The cleaning is similar to pH. Here we rinse everything off, obviously. We put it in a nitric acid and let it soak for 10 minutes to remove whatever's on it, mineral deposits and corrosion chemicals. If it happens to be oily, you can use methanol or an isopropyl alcohol to clean it off. There is a difference, though. Once you've done that, the ORP kind of is like a conductivity probe. It becomes, if you want to relate that way, polarized. So it needs to be set in and allowed to soak in tap water for about a half an hour or so to get that back out of the way, and so it can be used effectively again. Then you can put it in a known ORP solution, and if the value is in plus or minus 30 millivolts, then everything's good to go. It sounds like a pretty wide range, but ORP is not as accurate a measurement as pH. So plus or minus 30 millivolts is pretty tight for it, but not when you're thinking about comparing it to how accurate pH can be. If that doesn't work, if the nitric acid doesn't work, then you're stuck with something a little more difficult, where you might use an alumina powder or something to a little more aggressive to get the process off of the electrode. And again, after that, whatever you use on it, you're going to need to let it soak for about 30 minutes before you can use it for measurement again. Calibration is typically done just like pH, about once a month, and a little more often when it's more aggressive processes. And ORP is a one-point calibration. However, we usually use two solutions with different values, one to calibrate and one as a check. There's the two most common ORP solutions, types of solutions today are either a pre-made ORP solution or those that you can make yourself using pH buffers and a chemical called quinhydrone. And this is where you mix that quinhydrone in a pH 4 buffer or pH 7 buffer, and it creates a known millivolt value that you can use for calibration. Let's take a look at what that looks like.
I'm going to interrupt you 1 second, Nick. Thank you, guys. We're running at our hour. We understand. We just have a few more slides on there, and then we'll get in the Q&A. So sorry it's taken us a little bit longer, but sometimes that's what happens when you free lib stuff.
I talk faster, but I'm old. Quinhydrone, in fact, we've tried it here. You put a very little bit into a buffer, like a 4 buffer here, and until there are some particles left that have not dissolved. And I'm going to say that my electrode has a 3 molar KCl, and it's at 25 degrees C. So what I should expect to see is 253 millivolts. All right. If I'm using a pre-made solution, one thing I need to be careful of is that they usually put more than one reference electrode value on there. This one's, as you can see with the red arrows, it's calibrated, or the solution is calibrated against a 3 molar KCl, but they've also put the values of a hydrogen reference, and you need to know which one you're looking at so that you don't think, oh, I'm supposed to get 400 millivolts and all of a sudden I've got 600. It's that you're just looking at the wrong scale. But for these applications, these solutions, pre-made solutions, what you do need to know is what is the reference solution in your electrode. Is it a 3 molar or is it a 1 molar? And what's the particular reference system made reference to, 3 molar, 1 molar, whatever it may be. And in order, if you know that, then to determine the correct value that you should be reading, that's why we created this chart. We're going to take this as an example. Let's say you pre-made the solution for 350 millivolts. It was made against the 3 molar KCl. Your electrode is the 1 molar. So I'd expect to see a 22 millivolt difference because I have different references, which means instead of seeing the 350, I'm seeing 372. So it's not as direct as pH. You need to know your reference values. You need to know what you're measuring against, and because there will be an offset. But remember, that's such a small offset. It's plus 22 millivolts, and we have a plus or minus 30 millivolt error. So that's not too bad. But if this was had been calibrated against, all to the right it says SHE, that's the hydrogen electrode, it could be off by as much as 200 millivolts. So you really need to know the reference that your solution is made against and the reference value of your particular electrode. All right, we're getting there, guys. So basically, we've talked about the capacity for electron transfer, for redox, ORP. We talked about pH compensated ORP, which is a unique way to use it. Calibration, cleaning, that it's a one-point calibration, and there are those two types of solutions, either pre-made or the ones you make yourself. If you need information or you've got problems that you need to call in or email us about, these are the things you need to have already looked at, so that, because we're going to answer these questions. If you know these answers, what your specifications, what the problem is, what kind of installation issues, then we can help you more effectively get the right products or the right electrodes for your particular product. Because there are a whole lot of different electrodes to choose from, and so knowing your application and the problems your application face is going to help us get to the solution, something that will give you an accurate measurement and hopefully the longest life. Thank you all for your patience, and sorry we ran over a little bit.
Thank you, Nick. We do have a lot of questions that have been coming in throughout the webinar already, so we're going to start with those and then answer. Go ahead, if you've got more, answer them or type them into the Q&A or chat window. So the first couple questions that we have, kind of going all the way back to the beginning, Nick, you mentioned, and the customer's asking, what's the minimum water content that's needed in a solution for an accurate pH measurement?
Again, it has to be 5% of whatever the solution is. So the example I gave of jet fuel, there's basically no water in there, and they don't want water in there. So there's next to nothing. So whatever the process is, there needs to be at least 5% of it needs to be water.
Alrighty.
I'll add to that. If I'm measuring an acid, there's no water in there, and pH scale is basically within a range of a weak acid and a weak base. That's why there has to be water in there. When you get into the higher concentrations of acid and caustics, you're off the pH scale and you're into something like percent concentration conductivity.
Okay. How do we determine if our process actually has a temperature coefficient that you were talking about?
You would take 2 graph samples or 1 graph sample and measure it twice. Measure it at 25 degrees C and elevate it some fixed amount, 10 degrees C, something like that, and then do the calculation. How much did the pH change over that, whatever the range is, let's say over the 10 degrees C, and did it change positively or negatively? Typically, it's a negative a change, and it's typically small, 0.02, 0.03. The example here was a 0.028, I believe. But just take the measurement at 2 different temperatures and do the math. That's all you need to do.
Well, then how do I know which pH reading is correct? If the process pH runs at a higher temperature than the lab sample, what they're taking it as, how do I know if the process is right or the lab is correct?
That's sort of a mindset. A lot of folks say that they like to consider the online where it's giving you a different pH value at that higher temperature, that's actually what's going on. But typically it's a lower pH, and effectively the pH is higher, but it's not necessarily a negative effect on the process. What we've seen is 2 camps. One says, I want them to all match, so they put in the coefficient. The others say, I understand the difference, but I still want to see what it is online at that temperature. It has something to do with what you add or what you, if you're trying to neutralize, if you're adding something to it, online at temperature. But typically, the most common choice is to calculate it back to 25 degrees C. So what they're seeing in the lab is what they're seeing online. and the control and the lab measurement are matching, and that seems to work the best for everybody.
Is there a good recommended minimum flow and pressure in order to have good, accurate pH and ORP measurements?
pH and ORP basically measure wherever you put them. If there is nothing flowing, it's still going to measure the pH there. Flow rate for pH has to do with the strength of the glass electrode and how it's mounted. If it's mounted perpendicular to the flow, then obviously you're putting more stress on that glass electrode, but it has nothing to do with the measurement. Pressure has to do with the holders and the electrodes themselves. They're rated to a certain pressure, so staying within that is the key. But pH can be measured at very, very rapid flow rates and also higher pressures. It's the components that we're worrying about. I think we have a flow rate of like 2 meters per second, but that's again for the strength of the electrode, not for the measurement of it. The measurement is just, if it's in the solution, it'll make a measurement.
And when you agree, it also depends on the conductivity of the solution?
Yes. There is, and we talked about this, high purity water. Obviously, there's nothing there. There's no conductivity there. So I'm using the KCl from the reference electrode to make the electrochemical circuit. And if the flow rate is too fast, then it's going to wash that KCl past the measuring electrode so fast that there will be no continuity. In fact, you can, if you're measuring at a power plant, you can actually watch the noise increase to the point where it's not a measurement anymore by increasing the flow, because basically you're washing the salts away. So there, in that instance, you definitely need a slow flow rate, and typically it is, you slow it down to whenever it becomes stable. It's pretty slow. In fact, we say if you can take the top off of our holder and it doesn't overflow because it comes in the bottom and out the side, then it's the proper flow rate.
Okay, thank you guys. We have got a lot of questions. We will continue to answer them live here. But what we're also going to do, because we know your guys' time is very, it's very sensitive and stuff, we're going to put together these questions with answers and email them to all of you in the thank you for attending email that goes out to everybody. So we understand if you guys need to cut off, but for those of you, we'll still continue answering questions here. So going back into calibration, Nick, do you always have to use a 4 and a 7 pH buffer, or can you use a 4 and a 10 or a 4 and 9? And then also with that, when would you actually recommend using the higher buffer instead of the 7 buffer, the 9 or the 10?
Okay. Well, the trick is we're doing 2 electrodes, and you really want to zero and then work on the slope. So I would always start with a 7 pH buffer. That's 0. A lot of folks say, well, my measurement's up at the high end, so I want to use a caustic buffer for the slope part. All of that is possible. It's a linear slope. It's 59.16 millivolts between every pH step. The issue is not which buffer to use, but whether that buffer is accurate and stable or not. The 4 buffer is the most stable of all of them. It's a 4.01 or 4.00. I mean, you can't get much closer than that. The next most stable is the 7, which is a 6.86 or a traceable of 7.00. So those 2 are the most stable, and that's why we recommend them. Can you use others? Yes, but I wouldn't use a 4 and a 10. You haven't adjusted for a 0 yet. You haven't taken care of the 0. If you want to use a 10, that's fine, but again, you would use it fresh and immediately, because within, I won't say minutes, but within a very short period of time, CO2 is going to affect it, and it's going to cause it to be lower in value because it's going to make it add acid to it, make it bond in there and add an acid to it. You
showed in the calibration procedure roughly that When you clean it and you put it in a grab sample of the buffer and it's within 0.03 pH, you don't necessarily have to recalibrate it. It's good to go. So going off of that, if I'm looking at more of a caustic scrubber as my application and I want to maintain between a 0.2 pH unit in my calibrations, how do I determine the frequency in which I can calibrate or I need to calibrate?
Typically this is kind of a trial and error, but we had a scrubber application where we had a very common pH sensor, and the mode of maintenance was to have a bucket of acid near the site, or take one out, pull the probe, rinse it in the acid, rinse it off, and stick it in solution, and if it read within the range, 0.03 for the pH, they stuck it back online. Now they did this for over a period of time, and they realized that after, I think, I don't remember the exact days, but something like 2 weeks, 3 weeks, it was beyond that 0.03 accuracy, so it needed a little more attention. It needed to be either recalibrated, or rather than just rinsing it in the acid, it needed to use like a toothbrush or something to clean it off a little bit more. But if you use that as a rule of thumb, you can probably, since the process shouldn't be changing or is relatively the same, that what I'm doing is I'm cleaning off what is coating my probe to cause it to be a little less accurate than it should be, but I don't have to calibrate it because it hasn't aged, and that's what, or been deteriorated. It's just that it's the cleaning that needed to be done. So I can do that and save myself bringing out buffers and those sorts of things to the site.
Okay, I've read that there's a correlation between a charge of a solution and a pH, but it's not really a direct charge. Are you familiar with this, and have you heard of this? Maybe this has something to do with the pH compensated ORP?
I'm not sure I understand that. The charge of the solution, of the process?
I've read that there's a solution. In a solution, there's a value that correlates the pH. That's called the charge, and maybe this is the ionic content of it.
That's what they're talking about. If it's in the solution, remember you've got hydrogen ions, that's H+, that's the charge. And you have hydroxyl ions, which is OH negative. So depending on what solution you're in, you're going to have, I guess you can call it the charge, you're going to have either a positive or a negative charge, because there's going to be more of one ion prevalent than the other, either the H+ or the OH. That may be what we're talking about.
Sorry about that. Alrighty. For those refillable electrodes, why does the filling hole have to be open during measuring?
If you're talking about the electrode itself, I'm not sure that that's true. If they're pressurized, the filling hole doesn't need to be open. There are some probes that are pressurized mechanically, and so the back side or the part that looks like it's a filling hole is left open to create or help that pressure. But the filling hole does not have to be, if it's pressurized, the filling hole doesn't have to be left open. In fact, it might allow contaminants in there. So if I'm understanding your question correctly, it does not have to be left open.
Okay, back to calibration. If I'm being told to calibrate every 8 hours, and I personally think that it's a little too frequently, how do I, or what can I do, good practices, to develop our own validation chart to show them that it's really not needed?
That's where the diagnostics comes in handy, because if you're doing a calibration every 8 hours, every time you do a 2-point calibration, you would get an update on the slope and the asymmetry of the electrode. And let's say you did it every 8 hours for 3 or 4 days. You'd have 9 or 10 different steps showing the progression of the symmetry and the slope of that electrode, which says it's not changing at all or changing very little. So now, instead of every 8 hours, I'm going to do it every 16 hours, or eventually maybe once a day. And again, you can track the asymmetry and the slope to see what's happening with the reference and the measuring electrode. And from that, you'd be able to determine the best practices in order to maintain the accuracy would be something in between that 8 hours and some other value of, well, once every other day or once a week. But using that data, that would give you a line by which to track how effective is the probe, what's its life, how's it deteriorating. So that's what I would use.
Okay, going off with that same diagnostic information, we have someone that is asking, how can we diagnose if our reference electrode is poisoned?
Well, typically, that's where you're going to get that offset. You have a plus or minus, and for diagnostics, you have anywhere, depends on the analyzer, but typically plus or minus 120 millivolt offset. If you've cleaned it, you also can read the junction potential impedance, and if that's low, what it's supposed to be, then that's eliminated from the equation, and you're only talking about the internal solution now. That millivolt value that you get after you've done a 2-point calibration tells you how the internal is being affected or poisoned, if you will, depleted. It starts out and it's perfect or close, very, very close to zero. As it becomes contaminated, it begins to move away from that. When it's 30 millivolts, that's a half a pH, 60 millivolts a pH away, you can electronically calibrate for that error, but that probe is still that far away from being a good electrode, is that it has been poisoned a pH unit. So you can tell from that value, that millivolt value that you get after a 2-point calibration, how poisoned, if you will, it is.
Okay, switching gears again off of calibration, more to application. Do you have any experience measuring pH wort in beer fermentation? And main question is, does the yeast affect the pH probe, and if so, how?
We do have some information. I don't recall at the moment because we deal with some really good friends that make some really good product. But I can get that for you if we have your name and contact. I'll look that up because yes, we do have measured pH and wort. I'll have to research exactly how that affects it.
You don't remember everything?
I don't remember my name someday.
And now we're going to switch gears because there's just a couple more questions left, and it's going over to ORP side. Can we use 2 buffer solutions to check a redox electrode?
Yes. What typically they do is you either get 2 pre-made valued solutions, and you stick the probe in one and calibrate to it, and then rinse, and then put it in the second one to see if it's within plus or minus 30 millivolts as a test. You can do the same with pre-made solutions. You can do a pre-made 4 buffer and a pre-made 7 buffer, test it in the one, calibrate it to that, and then take it out, rinse it, and put it in the second one. If it's within plus or minus 30 millivolts, you're good to go.
So would you say that plus or minus 30 millivolts then would be a good accuracy for ORP?
Yes. Yes, it is.
Okay. And then you mentioned that a cation differential sensor. Do you guys have any training or other information on that sensor available?
We have a webinar on that. We have some training materials, hard copy material. Yes, we do.
Okay. Let's see if there's any other new ones that came in. I think that is it for all of them. Again, if I missed your question, we will contact you directly, either probably via email first, and then find out when a good time to talk is if you need to talk via phone. Thank you guys for joining us. Sorry we ran over our time. You do have our emails that have been up there now for about 20 minutes worth of questions. Sorry about that. You got Nick Nichols and you got mine, Sherilyn Marlowe, as well as if you need to call in directly, that's the 1-800 number for you guys to call Yokogawa. Again, thank you so much for your time, and sorry for going over. Have a good day. Yeah.